Hello everyone, welcome again to my exercise session. Today we will work on section 5.3 where we will apply methods of cylindrical shells. Now, the challenge will be pretty much the same with what we had in 5.2 where we will start with, let's review what we have at the time. We start with sketching the domain and then draw a typical line, rotate that with respect to axis of symmetry, axis of rotation, and then we come up with the area of cross-section and then come up with the integral to find the volume. This time, however, because we use cylindrical shell method, then we still come with the same. We start with the domain of integration. No, I think I should say the region that we're gonna rotate. Okay, and then we come up with a typical line. Let's do it together with number 3. So we will rotate with respect to y-axis here. So this is the axis rotation. Oops. Okay, then the typical line with shell method, the typical line has to be parallel to the axis of rotation. Okay, then when we rotate that, we will get a shell. Okay, now then the shell in this case will have radius x and the height in this case is equal to the value of the function y, which is the height is cosine x squared. By the way, cosine x squared is not the same to cosine squared x. Let me write it down. Cosine x squared is not equal to cosine squared x. Okay, they are not the same. The first one, we square the angle first and then apply the cosine. The second case, that's cosine x being squared. Now, so that's what the shell look like. What we do next is to unroll the shell so that we can see the rectangle. Of course, if you can skip that step, go ahead. We unroll the shell and then see, oh, what's the rectangle now? The rectangle has the height of cosine x squared I meant. And then the radius is x, but then when we unroll that, that's actually the circumference of the base. So the radius, the length here is 2 pi x, which is the circumference of that shell. Therefore, the shell area, in this case as a function of x, is equal to 2 pi x, which is the base of that rectangle. And the base of this rectangle, is actually circumference of that shell. Okay? The height of this rectangle is the height of that shell. Now, therefore, this is the base of that rectangle multiplied by the height of the rectangle. Okay, I'm not sure if highlighting this will help you to see, but I think for later part, I may not do that anymore. Okay. Then once we get the surface area of that rectangle, which is the shell, then the volume will be, the volume of the solid will be the integral of 2 pi from x equals to 0, the x will move to square root of x pi squared, square root of pi over 2, square root of pi over 2, from 0 to square root of pi over 2, x cosine x squared dx. Okay, now I will not do the integration anymore, but for the case like this, I will show you at least one step. I wonder if you know how to integrate this. Remember how to integrate this? Yes, that's right. We use u substitution. Okay, u equals to x squared, so du equals to 2x dx, and u at 0 is 0, u at pi over 2 is u at square root of pi over 2 is pi over 2. Therefore, now the volume becomes 2 pi integral from 0 to pi over 2 cosine x squared du over 2. To show you this part, x dx is this. That's how we get that du over 2. Okay, I'm sorry, it should be cosine u already. Cosine u already. Cosine u. Okay, I think when we compute this, we will end up with pi. But yeah, you show the work further. Okay, I think yeah, it will give us pi. Yeah, you still need to remember how to do your integration though. Okay, in this case, substitution method is from section 4.5. Now that's for number 3. Number 4, what if we rotate with respect to the x-axis? This is the axis of rotation, and if we want to use shell method, then the typical line must be parallel to it. Okay, from here we see, oh, the typical line must be y. Later on, the y will be from 0 to 1. Okay, I rotate that typical line. It's approximately like this. That y will be the radius, right? This is the radius. While the height of that shell later on will be, I think I need to rotate. You know what? Let's rotate this a little bit. So imagine if I screenshot this thing, just to help us see. Okay, and then, oops, no, and then I rotate this 90 degrees to the left. Now I hope you can see that the height of that shell now is, no, sorry, that some part of the graph is, yeah, it is correct. It's correct. Let me rotate that again. Rotate to the, yeah, to the left, 90 degrees. So why I feel like something's missing? Hold on. This is correct. Yeah. So from here to here, I'm sorry, I'm a bit confused. So if I rotate to the left 90, so this part here, where's my typical line? Why my typical line kind of changed? Yeah, the position of my typical line I think kind of changed. This is correct. Yeah. Anyway, let me see what I can do. Yeah, I want to see that. I want to say that this part here is coming from that y equals to 2 minus x, and then the lower is y equals to square root of x. So y equals to 2 minus x is the upper bound, minus square root of x is the lower bound, right? this guy, y equals to 2 minus x. Okay, and then this is y equals to square root of x as the lower bound. The problem is now, because we integrate with respect to y, we cannot use this one. We cannot use that one. We need to re-express the curves now as x as a function of y. Okay, so we cannot use this. We cannot use this because we will, and again, we will integrate with respect to y, right? We'll integrate with respect to y. I really wonder why I cannot rotate this. So this guy here will becomes x equals to y squared, while this guy becomes x equals to 2 minus y. Okay, now then you see again the line subtracted by the parabola. The line, which is 2 minus y, is subtracted by the parabola y squared. Okay, the graph on the right minus the graph on the left. The right bound minus the left bound. Okay, so again, so we will not use the red one. We will use, let me write it down again, because again we will integrate later on with respect to y. Okay, because we integrate with respect to y, we cannot have this guy inside in terms of x. Okay, let me erase this. We will use this guy. Now let's unroll our shell. When we unroll our shell, it will look like, of course, it's a rectangle. The height is 2 minus y minus y squared, while the base will be the circumference of that shell. The base will be the circumference of the shell, will be this guy here. Okay, this is the height, this is the height, this is the height. Now circumference of the shell will be 2 pi y. Therefore, the shell area now as a function of y will be 2 pi y times 2 minus y squared. Yeah, of course, if you can simplify a little bit, that would be nice. And then the volume, therefore, equals to 2 pi integral, well, because 2 pi is the coefficient, right? Integral. Now, take a look. The y will be moving from y equals to 0 to y equals to 1. That's how we know the integral, the interval of integration. That's from 0 to 1 of 2y minus y squared minus y cubed dy. Okay, I think the answer will be 1/3, 1/4, 5 over 12, 10 over 5 over 6. I don't know, you do it yourself. Okay, I think that one is quite easy to do. Number 3, because you need to do the u substitution, right? Okay, now so that's procedure. The first step is, don't forget, the first step is sketch the region that we're gonna rotate. Okay, and then draw the typical line so that you can come up with the shell. Second, you unroll that shell. You will see that the first step is the harder one. That's, even though we call that step 1, but in that step 1 you need to come up with the graph, and then you draw the typical line, and then you need to rotate that typical line parallel to axis of rotation. Okay, and then find the radius, what is the height, before you go to step 2. So this step 1 here, there's a lot of things. Okay, let me write it down. So the first one is sketch the region. They already sketched for us, but still we need to get draw the typical line, and then rotate that typical line. Okay, since they tell us to use cylindrical shell, then we know our typical line has to be parallel to the axis of rotation. Okay, and then rotate, and then you draw the shell, find radius and the height. Okay, and then from there we unroll the shell. That's our step 2, and then we go to construct the write down the shell area as a function of x before setting up the integration for the volume. Okay, so pretty much very similar to what we did in 5.2. Okay, now you will see this section here, as I said in my class, cylindrical shell is actually a supplement of disc or washer method. Okay, the things that may be hard if it is done by disc or washer method, then cylindrical shell actually perform very well. In fact, I can say more that if the typical line is parallel to the axis of rotation, then use shell method. Okay, if the typical line is perpendicular to the axis of rotation, then we use disc or washer method. Now, we still have some issue later on. Thomas, how do we know the typical line? But we talk about that later on. Okay, that's where the situation may become a bit more complicated. Okay, it depends on how the function given to us. Like here, y is a function of x, right? So x is the free variable, y depends on it. That's for number 3. Number 4, yes, there's still given y as a function of x, right? So for this question, maybe this method is better, maybe. Okay, but actually you will see that it's always doable using 2 methods, but one of them may be easier. Okay, if we try to do this using this method, let me take some time. Suppose I try to use this method. Then you see that I need to actually break it up into 2 integrals, because they intersect somewhere in between here. Okay, in fact, I think they intersect at 1. This is y equals to square root of x, and this is y equals to 2 minus x. So the typical line here has radius square root of x, right? Okay, so this will be radius square root of x, while the typical line here has radius 2 minus x. Okay, so the volume will be integral from 0 to 1 of pi radius squared dx, that's for the first part, plus integral from 1 to 2 of pi times 2 minus x squared dx. Okay, now when you go on, when you compute this, let me factor the pi out. When you compute this, you will see the result we get should be exactly the same if we use a shell method. Okay. That's for number 3 and 4. Now, as we go on, you see we have extra challenge, number 12, number 14. They don't give us the sketch of the graph or the graph. Then we need to do it ourselves. Now, in this case, you need to have faith in your instructor and in yourself that the graph given to you should be the one not too hard to graph, okay? The one that commonly given to us. So number 12, y equals to x squared. This is y equals to x squared. And then from x from 0 to 2, let's say this is my 2 here. And y equals to 4. Ah, that's new. And y equals to 4. This is y equals to 4. Oh, okay, so the region is this one then. And x equals to 0, right? They say x equals to 0. So maybe I highlight that. X equals to 0. This guy here is this guy. That's how I know that it refers to this region. Okay? Now then, we need to rotate this with respect to y-axis. Oh, the pink part there happens to be the the axis of rotation. Okay, so let's draw a typical line. That's x, and this is the typical line. You see that it is parallel to the axis of rotation. Okay, then we know it will become a shell method. They do tell us to use shell method though, so it's not that. How do I know we need to use shell method? Well, in this case, we know because that's what they tell us. Okay, now then, the radius is x. That one is easy. Now, the height, however, is y equals to 4 is the top part, and y equals to x squared is the bottom part. So the height will be 4 minus x squared. If then we unroll the shell, you see that the height is 4 minus x squared, and the base of that rectangle is the circumference of the shell. Okay, and the shell area as a function of x is now 2 pi x times 4 minus x squared. Okay, I think I will just, I will just do it like that. And as for the volume, you can do it yourself. That's 2 pi times integral. The x will be moving from 0 to 2, right? From 0 to 2, x 4 minus x squared dx. Okay, you compute yourself from there. But that's the setup. Yeah, yesterday when I did that section 5.2, I was a bit rushing because that was like half an hour before the beginning of my class. So I rushed and then I make some mistakes. But anyway, it's more about you practice your integration at the same time. Okay, that's for number 12. Wait a second. For number 14. We have y equals to 4x minus x squared. What does it look like? That's a parabola, opens down. That's an open down parabola. Okay, so if we can find the x intercept, that should be good enough, huh? So x 4 minus x. So the x intercepts are x equals to 0. X equals to 4. Okay, so let's try to sketch that. That's 0 and 4, that's the parabola. Approximately, that's the parabola. Oops. I don't know how high it goes though. We can find it out, but I don't think I need to what I need to, oh, y equals to x. So y equals to x looks like this, right? This is y equals to 4x minus x squared. This is y equals to x. We need to find out where they intersect. Y equals to 4x minus x squared equals to x. So 0 equals to x squared minus 3x. So they intersect at, when I factor, they intersect at 0. They intersect at x equals 0 and x equals to 3. So this is x equals to 3. Now the region that we need to deal with is then the one bounded by both. That's actually a very common question though. So if you usually have this kind of question, you are very normal, okay? Thomas, how do I know that's the region and not this region? How do I know that's not this region? Well, because the region, the blue region here, is bounded not only by the parabola and the line, but also by the x-axis, which they don't tell us. Okay? So the way we think is like, look for the region that is bounded only by those two, only by those given to us. Okay? That's how we know that it is not the blue highlight, but it's the pink one. Okay? Now, we rotate with respect to y-axis. Okay, this is my axis of rotation. So the typical line parallel to that has to be a function of x then, right? This is the shell. The radius is, from the axis of rotation, is x, and then the thickness or the height of that shell will be the upper bound, which is the parabola, minus the lower bound, which is x. So the height is 3x minus x squared. Now unroll that shell. The second step, unrolling the shell, only to help us to visualize that rectangle. So if you think you want to skip that step, go ahead. Just be very careful. Just very careful. I mean, if that takes you extra 1 minute to do this, I think I will do it just to give us the peace of mind that we have done our shell area function correctly. Okay, so there's a trade-off, like you write this step 2 here, you sketch and then write them down, so that when you go on to shell area as a function of x, you already have more confidence in what you do. Okay, this is 2 pi x times 3x minus x squared. So the volume will be 2 pi integral from, we have found that the interval of integration, x will be moving from 0 to 3, of x, 3x minus x squared dx. And then you go on from there. Is it okay? Now remember, we know that it is better done with shell method if the typical line that we draw is parallel to axis of rotation. Okay, so if they insist, the question insists that we need to use cylindrical shell, then you need to insist your typical line to be parallel to axis of rotation. Okay, so let's see, number 16. This time we will rotate about x-axis. Oh, still, we all rotate about x-axis still, huh? Okay, y equals to square root of x. X equals to 0. Oh, x equals to 0 is actually here. The y-axis. This is y-axis. And y equals to 2. Let me make it here. Y equals to 2 is here. we rotate with respect to x-axis. So this is our axis of rotation. Oh, I see. Then our typical line, if we want to do shell method, then our typical line must be y equals something, right? Let's say this is the typical line, y equals something. Okay. And the y will be moving from 0 to 2 because this is the region of rotation, the region that we will rotate. Now, if I rotate that typical line, the radius will be y. Okay, but the thickness here will be y equals square root of x. But, let me slow down. But, notice that we will integrate with respect to y. So we cannot use this one. We cannot use this one. We need to replace that to x as a function of y case. Okay, so we don't use that one. We will use x equals to y squared instead. So, if we unroll our shell, let me unroll it this way now. So, this part here will be our circumference. Okay, and the base is y squared. Okay. Yeah, we can also we can also see it this way, right? You see? You see the base is 2 pi y, the height is y squared. Okay, just different perspective, right? Oops, sorry. Just different perspective. Therefore, now we go on, the shell area as a function of y is 2 pi y times y squared. Oh, that's one of the easiest. That's one of the easiest integration we have today. So it's not about the integration, it's about the setup, as you will see. As you have seen, 2 pi integral from 0 to 2 y times y squared. Of course, then when you integrate that as a y cube, right? That's for number 16. Let me go on. Number 20. We will rotate with respect to x-axis later on. So x plus y equals to 4. That's a line. I don't like that. That's a line like this maybe. Okay, so the x-intercept and y-intercept are both 4, 0, 0, 4. X equals to, this one is challenging. X equals to y squared minus 4y plus 4. So that's equals to y minus 2 squared. Y minus 2 squared. So the vertex is 0, negative 0, 2. So it looks like this. Like that. So x equals to y minus 2 squared, but x also equals to 4 minus y. Yeah, we need to find the intersection here, right? We need to find the intersection there. Okay, how do we do this? So this will be y squared minus 4y plus 4 equals to 4 minus y. The 4 cancels, so I have y squared minus 3y equals to 0. Y times y minus 3 equals 0. Y equals 0. Oh, okay, so this is the y equals to 0. The coordinate here is 4, 0, right? So this is y equals to 0. And then y equals to 3. This is our y equals to 3. So the region later on we'll have y moving from 0 to 3. Okay, yeah, the axis of rotation is x-axis, right? This is this x-axis here. So our typical line, let's call this is our y. Our typical line later on will be moving from 0 to 3. Now let's see, if I roll that typical line, rotate that, and you see our radius is y, but the thickness will be the line, which is x equals to 4 minus y, subtracted by the parabola, which is y squared plus 4y plus 4. That's the height of the shell. Okay, maybe you can see it better if I rotate it this way. Okay, so that's the line minus the parabola, right? The line minus the parabola. Of course, simplify first before we go further. The 4 will cancel. We have negative y squared plus 3y. Okay, then if we unroll that shell, we will get the base, or the base of that rectangle will be the circumference of the shell. That's 2 pi y, and the height of this is negative y squared plus 3y. Therefore, the surface area of the shell as a function of y will be 2 pi y times negative y squared plus 3. The volume, therefore, 2 pi integral, you see the y move from 0 to 3, right? From 0 to 3 of y times, I'm sorry, I'm missing a y here. I'm missing a y here. Yeah. If I make that kind of mistakes, you do that correction yourself, okay? I'm not preparing. Honestly, when I do these videos, I'm not preparing anything. I just see, oh, I think this question is interesting. I think my students can learn from this question. So that's why I chose them. But I myself purposely not preparing in advance what's the answer. Because if there's any difficulty, I want to be able to handle it without a full preparation like my students. You know, like when you take a test, you know the concepts, right? Yeah, you know the concepts, but I don't want to appear to you as somebody who's like, oh, I know everything right away. I do make mistakes. I do. Take a look in my 5.2, then you see that. Good thing those are the mistakes I make in my 5.2 videos are not technical mistakes. It's like miscomputation here and there. But good thing I catch them. I know I was rushing, so it's like, oh, maybe I make mistakes. So let me check my work. And then when I check, oops, there are three mistakes, you know. Okay, well, anyway, yeah, if I do make mistake here, just you do the correction. I know I don't make technical mistake. If I make technical mistake, then I have to scrap this video. I need to do it all over again. You know, but if it is just little computational mistake, I'm missing a y, as long as I continue with, it's just a technical, right? If I go on with correct technique, then I will just skip it. Okay, let's go on. Number 23, number 24. Now we rotate the region about something else. They give us the graph, okay? They give us the graph. Now we rotate with respect to number 23. We rotate with respect to x equals to negative 2. Oh, just leave it there. Axis of rotation, x equals to negative 2 is approximately here. Right? That's the axis of rotation. So the typical line, if we want to do shell method, the typical line will be parallel to the axis of rotation, call that x, which if I rotate, it will look like this. Oops, too big. Okay, now the thing is, what is then the radius of this shell? We need to be a bit careful. Notice that this is x equals to -2. So the distance from this axis of rotation to here is actually, this is x, right? You see, that's x. But this is 2. Okay, so the radius is 2 plus x. Okay, while the height is the same, which is why the height is 4x minus x squared. The one you need to be careful is when the axis of rotation is no longer x-axis or y-axis, then you may need to add something or subtract something or some modification. Okay, but then once it is done, well, we go back to normal storyline. Okay, we unroll the shell. The circumference now is 2 pi times the radius, but the radius now is 2 plus x, and the height is 4x minus x squared. So the shell area as a function of x will be 2 pi times 2 plus x times 4x minus x squared. Okay, well, that's a polynomial, right? So earlier, when I write the volume, that I write it as 2 pi integral from 0 to 4. But if you know that you need to FOIL that before the integration, then do that first. Okay, so this is 2 pi times, what is that? 8x minus x squared minus 2x squared plus 4x squared, that's plus 2x squared minus x cubed. Like that. Then after that you put it here. Is it right? Yeah, 8x plus 2x squared minus x cubed dx. And then from there you go on yourself. Okay, that's if we rotate about x equals to -2. How about if we rotate about y equals to -1? Y equals to -1, from the shape, then it looks like this. It's here. Okay, but since this is y equals to -1, oops, too big. Now, if we insist to use shell method, in my opinion, for this case, I think it's better to use washer method. Okay, but if we insist using shell method, you know what? Before I go on, let me copy this first. Later on, I will use washer method next to it. Okay, so if we have this typical line here parallel to the axis of rotation, then the radius will be that y plus 1, right? So let's approximately, it looks like this. You don't need to graph that to scale though, but the most important one is you have the feeling, oh, I need to do this, I need to do this. Now, then the radius of the shell is y plus 1. This is y equals to 1. The length is 1, and the length here is y. Okay, while the thickness of that shell is, the upper bound is, oh, I think I need to, it has to be in terms of y. So this is now x equals to y to the 1/3, and this is now x equals to y squared. So the thickness or the height of that shell later on will be the curve on the right, which is y cubed, minus the curve, I'm sorry, y to the 1/3, not y cubed, minus the curve on the left, which is y squared. Therefore, when I unroll that rectangle sideways, okay, the circumference of that shell becomes the length of the base, 2 pi times 1 plus y, and then the height is y to the 1/3 minus y squared. Okay? Okay, I have 5 more questions, actually 7 more questions. Now, then the shell area as a function of y will be 2 pi 1 plus y times y 1/3 minus y squared. Okay? You know what? Because I'm about to do that with this method or washer method, let me compute this and show that we're supposed to get the same result. The volume will be 2 pi integral from y equals to 0 to y equals to 1. This is y equals to 1, right? From 0 to 1, if I FOIL that, I get y to the 1/3 minus y squared plus y to the 4/3 minus y cubed dy. Let me compute this, okay? Bear with me. So this is 2 pi times that becomes 4/3, 3/4 y to the 4/3. But I do 0 to, so let me skip a little step. This is minus 1/3 plus 3/7 minus 1/4. Yeah, I skipped one step, or maybe 2 steps. So what will this be? This guy minus this guy is 1, so this 2/3 plus 3/7, 9, 14, 23/21. So 23/21, that is 46 pi over 21. Okay, now to check if I have done it right, I hope to check if I have done it right, let me do the washer method. Okay, let me do washer method. That's way too far to the right. Let me move down a little bit here, and then I'm gonna do it here. So I still a little space here by washer. Okay, so y equals to 1 is negative 1 is here. Okay, but if I use washer method, this is my typical line. Notice that it is perpendicular to the axis of rotation. Okay, axis rotation, I usually use this color. Let me use this color now. This is my axis of rotation, such that when I rotate this, I hope now you see the washer. The bigger circle minus the smaller circle. Okay, the bigger circle, the smaller circle. The bigger circle has this radius 1 plus square root of x. So the bigger circle has radius 1 plus y to the 1/2, while the smaller circle is 1 plus x cubed. Why did I write y to the 1/2 there? That's supposed to be x to the 1/2. I'm sorry. Should be x to the 1/2. So the smaller circle has radius 1 plus x cubed. Okay, so the area of the ring is equals to pi big radius squared minus pi small radius squared. I will factor the pi, You can do the FOIL if you want, right? I think that's what I'll do. I will FOIL that. So this is 1 plus 2x to the 1/2 plus x minus 1 minus 2x cubed plus x to the 6. Gada bum, gada boom. I get negative x to the 6 minus 2x cubed plus x plus 2x to the 1/2. The 1 cancels. The 1 cancels. Okay, so the volume is now equals to, I hardly do computation, right? But if I compute it this way, I hope I get that same answer. If not, then I must have done some miscomputation somewhere. That's quite embarrassing because this happens on the recorded situation. But hey, you know what? Welcome to life, right? If I make mistake, admit it and fix it, and of course move on, right? People do make mistakes. Okay. In other words, if you do make mistakes, that's okay. Don't worry about it. Okay. But focus on the setup. Okay. Focus on the setup. Focus on the technicality, and with more practice, especially with more mistakes that you make, then you learn. Okay, I make mistake in this kind of case here. I make a mistake in the other kind of case before, and you learn from your mistakes and be a better person. Okay. So don't be afraid with mistakes. Be afraid that you are not capable to take criticism if you cannot make a mistake and fix it. Okay, now nobody should expect you to be a perfect person. Not even your boyfriend, girlfriend. Okay, yeah. Let's go on. So this is negative 1 over, I skip one step. Okay, and then this is minus 1/2 plus 1/2, and then this is plus 4 over 3. So when I compute this, 1/2 cancel 1/2. So 4 over 3 minus 1 over 7, that's 28 minus 3 over 21. Hey, something not right. I get 25 over 21. Hey, it's different. I get the 21 right. I get the 21 right, but the 25 is not. Where did I make mistake? Okay, let's check. That's how I learn anyway. Okay, so let's check. Let's come back to here. I know I definitely make a mistake somewhere. And that's because I skip a step, then I miss it. Let's come back here. So this is 1 plus y, 2 pi of that. Okay, that's 1 plus x, 1 plus y, and this is y to the 1/3 minus y squared. Y to the 1/3 y squared. So let's see if I FOIL that correctly. That's y cubed. So when I integrate that, 4 over 3, the reciprocal is 3/4. 1/3, 3, 7, 1/4. So let's see. So 3/4 minus 1/4 is 1. Minus 1/3 is 2/3 plus 3 over 7. 14 plus 9, that's 23 over 21. So I'm correct for that one. Do I make mistake here? 1, 2, and then x minus 1, 2x cubed. Did I set it up right? So radius is 1 plus square root of x, so that's right. 1 plus x cubed, that's right. When I FOIL, this is correct. When I FOIL, this is correct. Negative that, negative this. So when I integrate, This is negative 2 over 4, so that's 1/2, that's 1/2. Hold on, this may be wrong. 2 times 2 over 3, that's also correct. So the positive 1/2 minus 1/2, that's cancel. 4 over 3 is 21 minus 3. That's why. Let me stop the recording first and see what mistake I made. I think I found my mistake. My mistake here, when I subtract 3/4 minus 1/4, I think earlier I called that 1. It's supposed to be 1/2. 3/4 minus 1/4 minus 1/3 plus 3 over 7. This is 1/2. 1/2 minus 1/3 is 1/6 plus 3 over 7. That's 7 plus 18 over, what am I doing? Over 42, 7 over 42. So I get 25 over 42, not 23 over 21. That's my mistake. Sorry. See, if you try to do it too fast. I think I'm getting a lot older. So this is 25 over 42. Oh, good thing I check. Otherwise, I leave it incorrect. 42 and 2 cancels, it becomes 21. So my washer method is already correct. Okay. But you see, I make no mistake in my technicality when I integrate that. Because I did it too fast. Okay. Well, anyway, let me continue. We have now this y equals to square root of x, y equals to square root of x, so that's what it looks like. Okay, and x equals to 2y, y equals to 1/2 x, so the slope is 1/2, so y equals to 1/2 x, or you can call that x equals to 2y, and this is y equals to square root of x, or you can call that x equals to y squared. I don't know which one I will need later on. Let me just draw it like that for now. Oh, now I see the issue. I need to rotate about x equals to 5. Okay, so let me move this here and then make it a bit smaller. Okay, x equals to 5 should be somewhere around here. I need to know where they meet though. Where's the intersection? The region for sure is this one. Right, that's the region. Okay, where do they meet? So x equals to y equals to 1/2 x, y equals to 1/2 x, which is equal to square root of x. So if I square both sides, I get 1/4 x squared equals to x. So either x equals to 0 or x equals to 4. Okay, this is 4. I mean, you compute it yourself, right? So if I have a typical line here, this is x, and remember this is x equals to 5, right? So the radius is now, this is 5, this is x, so the radius of that shell, is now 5 minus x, right? The radius of this shell is 5 minus x. This guy here is 5 minus x. The height, on the other hand, it's on the easier side. That's square root of x minus 1/2 x. Okay, I'm having a class coming, so let me go a bit faster. I still want to finish this though. Okay, so if I unroll that shell, my base, which is the circumference of the shell, will be 2 pi times 5 minus x, while the height is x to the 1/2 minus 1/2 x. So the shell area as a function of x is now 2 pi times 5 minus x times x to the 1/2 minus 1/2 x. Okay, consequently, then the volume is equal to 2 pi integral, our x is moving from 0 to 4, right? And then 5 minus x, x to the 1/2 minus 1/2 x. Of course, you will FOIL that and then integrate from there. Okay. Number 30, we have x equals to 2y squared. What does it look like? A parabola opens in the positive x-axis. So it looks like this. And x equals to y squared plus 1. Oh, I see. So now the x-intercept is 1, 0, but the parabola opens this way. So they intersect somewhere. We can compute that now. X equals to 2y squared equals to y squared plus 1. So, plus 1. So y squared equals to 1, y equals to plus minus 1. Okay, so this is at y equals to 1. This is y equals to -1. But, we rotate that with respect to y equals to -2. So if we have a typical line, let's say the typical line is here, then this is y, right? This is y. You know what? This is y here. It's the typical line. So the radius will be this is equals to 2 plus y, right? Okay, and then the thickness will be the upper one. Maybe I write it here. The height will be y squared plus 1 minus 2y squared, which is 1 minus y squared. Okay, so if I unroll that rectangle, the circumference of the base of the shell will be 2 pi times 2 plus y. The y will be moving from -1 to 1. Okay, while the height is 1 minus y squared after I subtract. Okay, so the shell area as a function of y will be 2 pi integral from -1 to 1 of 2 plus y times 1 minus y squared dy. Okay, let me do the computation here. Okay, I assume my setup is correct. Honestly, I'm a bit rushing because I have another class in 1 hour, but I need to drive for 1 hour. Okay, I'll be a little bit late for my office hour. My office hour starts in 1 hour, but it's in Southgate area. The traffic on Friday afternoon is just ridiculous. Well, anyway, but I want to show you something here. That's why let me show you the integration. So this is 2 pi times integral from -1 to 1. Notice the following. Notice that the interval of integration is opposite. If I can identify the integrand as an even, then I will fold it, make it double. But if it is odd, it becomes 0, right? Okay, now if I FOIL this, I don't need to do it this way though, but this is one way to do it. This is 2 minus 2y squared plus y minus y cubed dy, right? Okay, now because the domain of integration are opposite intervals, the interval opposite numbers, right? Okay, so as long as it is odd function, they will become 0. Do you see that? I mean, you can try to do this integration in full, but you will see those last two terms will become 0. Okay, and we end up with the guy in the middle here. I can factor the 2 out. You see that? And I can fold this further. I fold it from integral from 0 to 1, 1 minus y squared dy. Okay, so this will be 8 pi times, I think if I integrate that, I will get 2/3. So the final answer is 16 pi over 3. Okay? Yeah, the reason I want to go over that is because to show you that since the domain of integration, the interval of integration is opposite, interval with opposite numbers, opposite endpoints, then you can make use of even odd cases. You FOIL them first and then see, oh, you know what, this is an odd function. Then if I integrate that terms, it becomes 0. Oh, that's an even function, so if I integrate, it becomes double. Okay? Now, I was planning to do 3 problems from here, but I think I will just do 2 of them. This, I think I will do number 50 and 52 then. Okay, number 50. Number 50. Let me take this. I do another screenshot so that I can just work on this. So number 50, let me see where they intersect. So I need to find out this thing. Okay, so y is equal to 4x minus x squared. That is equals to y equals to x. So 3x minus x squared equals to 0. Consequently, then you will see x equals to 0, x equals to 3. So this is 3 here. Okay, I rotate about the y-axis. Oh, here, use any method. Now, then we have the. Then this is where I want to show you the flexibility where the shell method is actually the supplement. Okay, draw the typical line first. Oh, it's parallel to axis of rotation, so we will use shell method because when we rotate with respect to with that axis of rotation, we will get the shell. Okay, and therefore when you unroll that, you will see, oh, the radius is x. The radius of that shell is x, so the circumference is 2 pi x. The height is 4x minus x squared minus x, which will give us 3x minus x squared. So the area as a function, the shell area as a function of x will be 2 pi x times 3x minus x squared. The volume, therefore, you can tell I'm rushing, right? 2 pi integral from 0 to 3 of x times 3x minus x squared dx. Okay, and then you continue from there. Now, next one, we have this function bounded by x equals to 2, but we rotate about, oh, where do they intersect? Where do they intersect? We know the x is 2, but how about the y's? The y's, so x equals to 2, but x also equals to 3y minus y squared. So that's y squared minus 3y plus 2 equals to 0. So y minus 2, y minus 1. Oh, okay. So they intersect at y equals 1, y equals to 2. Now, the thing is, I will rotate with respect to y equals to 3. Y equals to 3 is somewhere around here. Okay, that's y equals to 3. I think it's too long. Let me erase a little bit. I need some space. Okay, so if I pick a typical line here, that's y, right? Oh, that will be a shell method again, huh? If that's y, then the radius will be the whole 3 minus y. 3 minus, the whole thing is 3. This is y. So this guy here is 3 minus y. While the thickness is let me draw the shell. I kind of like rushing too much there. The quality is so bad to my guess later on. So it will look like this. Okay, so the function on the right is 3y minus y squared minus 2. Okay. So if I unroll the shell, the thickness will be 3y minus y squared minus 2, while the circumference of the shell will be 2 pi times 3 minus y. Therefore, the shell area as a function of y will be 2 pi times 3 minus y, 3y minus y squared minus 2. Now, the volume of generated solid is 2 pi integral from 1 to 2, 3 minus y, 3y minus y squared minus 2 dy. Okay, in both cases it's still a shell method, huh? But remember, the way we think is we draw the typical line based on the function. Here the function is x equals to a function of y. So y is a free variable, right? Okay, so I draw a line y equals to something. That's how I know that's the typical line. Okay, let's go on. Number 54, that's the last two questions. Okay, so the region bounded by the given curves rotated about the specified axis. Find the volume of the resulting solid by any method. By any method. Okay, so I have this function. I need to know what the graph looks like. This is upside down parabola. Let's find the x-axis. So I factor the negative and then I factor the trinomial. I think that's minus 4 and minus 2. Huh? Okay, so I get y, I'm sorry. So for the x-intercept, I set the y equals to 0. So x equals to 4, x equals to 2. It is an upside down parabola. Upside down parabola. This is 2, this is 4. Okay, about x-axis. So this is my axis rotation. This is my axis of rotation. But the function is given as y as a function of x. So my typical line will be this line here. This is my typical line, right? Y equals to negative x squared plus 6x minus 8. Okay, so if that's the typical line and I rotate, as you can see, we get a disk. Okay, the radius of that disk is negative x squared plus 6x minus 8, which actually we already factored that way. I don't know how much it will be helpful though, but then the area of that disk, that's the radius, right? That's negative x squared plus 6x minus 8. So the area of that disk as a function of x is pi r squared. Notice that we already did the factoring there. The negative squared will cancel. I will get x minus 4 squared. I don't know how much this will help us later on in our computation. But at least we come up with the volume setup. That's integral from 2 to 4 of x minus 4 squared, x minus 2 squared dx. Okay, you know what? Let me just do it. Instead of doing it there, then I prefer to simplify it from there. So this is pi times x squared minus 8x plus 16 x squared minus 4x plus 4. If I FOIL that further, I get x to the 4th. For x cubed, that will be negative 4 minus 8. That's negative 12x cubed. For x squared, that's 4 plus 32 plus 16. So what's that only? 52 plus 52x squared. As for the x, negative 32, negative 64. That's minus 96x. And then finally plus 64. Okay, so this becomes then x to the 4th minus 12x cubed plus 52x squared minus 96x plus 64 dx. Then you compute that further yourself. Okay, at least I show you how to do that. It's basically do the perfect square twice, right, for each one of them, and then you FOIL them. Okay, how you FOIL them, then you do it long way maybe. Okay, yeah, you do it long way maybe. I may have made mistake, but I don't think so though. So negative 4 minus 8 is negative 12. 4 plus 32, that's 36, plus 16, that's 52. As for x, that's negative 32 minus 64. And then 6. Yeah, that's right. Okay, number 56, the last one. The reason I choose this question here because you may not have seen this too much. To be honest with you, I don't think I'm gonna ask you that kind of function or that kind of curve. But if you did your pre-calculus far enough, then you will see this is actually a hyperbola. Okay, centered at origin. Okay, opens to positive and negative y-axis. It is a hyperbola that looks like this approximately. Okay, it's bounded by this hyperbola and y equals to 2, so this is y equals to 2. This is y squared minus x squared equals to 1, so I don't need the bottom one. And then I rotate that about the y-axis. So it's this region rotated with respect to the y-axis. The thing is, the y-axis is here. So when I rotate that, it will look like just a ball, maybe, right? It looks like this. You see what I mean? Okay, I may overdraw that. Okay. So which way is better to do this? Let me do the typical line. The typical line. See, the thing is like with this guy here, I can go either way. I can go either way. But I think let's do the shell method. Okay, let's draw a parallel line. Okay, to the axis of rotation. Let's call this x. So if that's x, I need to solve for y. Y squared equals to 1 plus x squared. Y will be the positive branch. Right? The positive branch of that. Okay, now the radius will be x and the thickness will be 2 minus square root of 1 plus x squared. Okay, now even though the region is from, I think this is from what, -1 to 1, right? But due to the rotation, we just need to integrate from 0 to 1. If I unroll the shell, I get 2 pi x as the circumference, and then the height will be 2 minus square root of 1 plus x squared. Okay, so the shell area will be 2 pi x times 2 minus square root of 1 plus x squared. Then the volume is equal to 2 pi integral from 0 to 1, right? They intersect at 1. Let's make sure. Or maybe not 1. I'm actually not sure now. Y squared minus x squared equals to 1, but the y is to 4 minus x squared equals to 1. Oh no, x squared equals to 3, so that's square root of 3. From 0 to square root of 3 of x, 2 minus square root of 1 minus x squared dx. Now you may get a bit confused on how to do this. Distribute first. Let's see. I want to show you how this can be done quite well. Distribute first. Integral from radical 0 to radical 3 of 2x minus x square root of 1 plus x squared dx. Now, it's actually easy to integrate this part. This integral of 2x is just x squared. I believe your issue is what happened to this ugly guy here, right? But you will see that's actually doable by u substitution. Okay, let me break it out. This is 2 pi integral from 0 to square root of 3 of 2x dx minus 2 pi integral 0 to square root of 3 x square root of 1 plus x squared dx. U substitution 1 plus x squared du is 2x dx. U at 0 is 1. U at radical 3 is 4. I feel I'm too fast because I'm rushing, but you slow down, you pause it and see what I did. Okay, now the first integral, we just integrated as usual, is 2 pi times x squared from 0 to radical 3. You will see that's 2 pi times 3 minus 0, which is 6 pi for the first part, but I need to keep them intact. Okay, so this is minus, okay, pi times integral from 1 to 4 of u to the 1/2 du. My du is actually obtained from here. I try to get them. This is my 2x dx. Now becomes my du. Okay, that's why outside is only pi. Okay, and then inside we have that. Okay, minus pi times 2 over 3 u to the 3/2 from 1 to 4. That's 2 pi over 3, 8 minus 1. That's 7/14 pi over 3. So 6 pi minus 14 pi over 3. 18 pi over 3, 18, so that's 4 pi over 3 then, huh? Okay. Now, the last question, number 56, actually also doable using, let's try. I believe that's doable using this method. Okay, let's try. So it looks like this. I just take the top branch. Okay, it looks like this. They intersect at radical 3. But if I say this is my typical line here, about y-axis, if this is my typical line, okay, then when I rotate that, I get that this. The radius is equals to x, right? Okay, so area of that this respect to x is pi x squared. But notice that x squared is just 1 y squared minus 1. Oh, that's actually really nice, huh? Okay, so the volume turns out to be a lot easier to do this way. Seems like the volume will be pi integral from y equals to 1 to y equals to 2 of y squared minus 1 dy. Oh, that's a lot easier to do. That's a lot easier to do. Okay, this is y 1/3 y cubed minus y from 1 to 2. So that's 8 over 3 minus 2 minus 1/3 minus 1. So that's 2 over 3 plus 2 over 3. Oh yeah, that's 4 pi over 3. Now I didn't expect that to be that nice though. I didn't expect it to be that nice. But you see that the same question number 56 here is actually doable using two different methods. Okay, I think what makes this method here becomes a lot easier is because when I square that x squared, when I square the x squared, happens to be something we already have. You see what I mean? That's like ready to use, right? I think that's the reason. That's the reason. But I didn't see that until I work it out. You know, this is, I believe this is a good example to tell you that, yes, even after you sketch it, you may not know what is actually a better way to do it. Okay, I was expecting the shell method is actually much easier. It turns out that this method is better. Okay, anyway, let me stop here.